think. Okay, sounds good. All right. Hi, everyone. I'm Fabio Pacucci from the CFA, and today I will give a very short review of some of the science that could be enabled by Axis in the future, specifically about black hole physics and black hole observations. So, okay. So in this talk, I will be mostly talking about three different populations of black holes. Specifically at the beginning, we'll be talking about how Axis can contribute in detecting the first population of black holes that were seeded at redshift higher than 15. Then I will move on to study how black hole accretion and mergers from another side of the spectrum changed as a function of cosmic time, and how Axis can also enable the study of this accretion. And finally, I will go into much closer spaces and explain how Axis and other missions can help detecting putative wandering intermediate mass black holes in the Milky Way. So these are smaller black holes compared to the supermassive black hole at the center, but they are off-center. So they are just wandering and accreting from the interstellar medium. So let's get started. There is a big problem in cosmology and astrophysics since probably 20 years at this point. We're discovering farther and farther quasars. This is the farthest quasar discovered so far at redshift 7.6. And these are supermassive black hole on the 10 to the 9 solar mass scale. So the problem is that we don't know exactly how they grew up so rapidly. In fact, from seeding, so a redshift about 20 or 30, to these observations, there is also only half a billion years. So there are many ways in which these seeds can be formed. If you start from a low mass seed, so a remnant of a POP3 star, typically on 100 solar mass scale, then it's very, very challenging to reach the 10 to the 9 solar mass scale by redshift 7 or so, because there is the Eddington limit. Black holes can't grow much rapid than the Eddington limit, but there are also many theories that allow super Eddington accretion rates or hyper Eddington accretion rates for short periods of time. So in that case, it could be possible to go from a POP3 remnant to a quasar, full-fledged quasar at redshift 7 or so. An alternative is that we can form seeds, heavy seeds already on the 10 to the 4 or 10 to the 5 solar mass scale. And there are many ways that have been studied in literature to form these objects already at redshift 20 to 30. And in this talk, mostly I will be talking about DCBHs or direct collapse black holes. To form such objects, you need metal-free gas, you need an atomic cooling halo, and an influx of high-energy photons, especially Lyman-Barnett photons in a specific window, rest frame of the electromagnetic spectrum. Basically, you are avoiding cooling and fragmentation. So instead of forming a lot of stars, you form a DCBH, a direct collapse black hole. So basically, what we wanted to understand a few years ago is how, what are the emission characteristics of these accreting first black holes, and how can we detect them specifically with Axis in this talk, of course. So this is quite an old simulation. This is basically 7 years ago right now. And this simulation is showing how the spectral energy distribution of a heavy seed, a DCBHs, changes as a function of time. And this is original 10 to the 5 solar masses seed. As you can see, here goes from the infrared, mid-infrared to high energy X-rays here. And this is in a zero metallicity environment. What you can see now is that both the JWST and in the X-rays marginally the Chandra fills out, but much better links and axes should be able to detect these sources for most of their accretion time. So of course, in this talk, I will be focusing on axis and in general, the high energy regime. So this is a zoom in of the previous simulation. Assuming a Compton thin environment in the host galaxy, you can see that both links and axis, assuming the intermediate survey, they should be able to observe most of the accretion process on a typical heavy seed at high redshift. With a Compton thick scenario, so assuming that there is a lot of gas in the host galaxy, we see that also axis and links should be really able to detect these sources, while shallower surveys like the ones expected from Athena shouldn't be able to observe these heavily Compton thick sources. So classic DCBH SED, so spectral energy distribution, in the X-ray should be easily detectable as in the infrared. But in an SED with a very large absorbing column density, so assuming that there is a lot of gas in the host galaxy, as I said before, in the X-ray should be still detectable with axis. And in the infrared also possibly detectable in the highest accretion part, so when these sources are the most luminous, the most bright. So basically in the search in the next decade, to obtain an equivalent detection of heavy seeds, we need to probe mass scales of 10 to the 5 solar masses at redshift higher than 10. So now with JWST, we're routinely detecting galaxies that are possibly at redshift 13 or redshift 17 on archive just last night. But it's important to understand that we need to probe much smaller mass scales, so 10 to the 5 solar masses at redshift certainly higher than 10, but possibly around 20, to actually be able to detect and discriminate between seeding. And in particular, this was a table that we compiled for an Astro 2020 white paper with the requirements that are required in the infrared, in the X-rays. So with the JWST, it's possible that we will detect 1 to 10 per square degree of DCBHs. With axis, it could be possible that we detect more than them. With the intermediate survey, we should be able to detect more than 10 per square degree. But I should warn you that these predictions are very, very dependent on the model for DCBHs that you're using and consequently on the number density. Number density oscillate between models by several orders of magnitude. So this expectation could be easily 10 times lower or even 10 times higher than that. So regarding axis, where am I? Sorry. Regarding axis, do you still see this?
Yes, yeah, looks
okay.
good.
Oh yeah, I just lost my screen for some reason. Regarding axis, the higher angular resolution and the possibility to detect, as I was saying, heavily Compton thick sources should be really important to detect and discriminate between seeding model at high redshift. And in particular, the search in this decade could proceed with the pre-selection, the candidate selection with the current dataset, and then a deeper look at these sources, both with the JWST for the spectrum and with axis, for example, to detect X-rays, which would be really a smoking gun for the presence of an accreting black hole. So now I will be talking about how more in generally X-rays and partially gravitational wave observation will be important to understand how black hole grows across cosmic time. And of course, I don't have time to go into the details of the model, but in general, mass growth rates both for gas accretion and for mergers, are calculated from quasar luminosity functions up to the highest redshift that was available a couple of years ago, and mergers are calculated with a merger tree approach. But again, I don't have time to go into details, but feel free to ask me more details later. So this is the general picture that we obtained in this model. On the x-axis, you have the log of the black hole mass. On the vertical axis, you have the redshift, so basically cosmic time from the local universe to the farthest galaxies that were observed a couple of years ago. So wherever you see blue, it means that most of the mass is being added by accretion, while wherever you see red, most of the mass is being added via mergers. And these dot dashed line indicate where mass growth by accretion equals mass growth by a merger. So specifically, you see that at low mass, low redshift, most of the mass growth happens via accretion, high mass, low redshift via mergers, low mass and high redshift via mergers, and high mass, high redshift via accretion. So why do we care about the growth channel? Well, we care, of course, because that determines how we're going to observe these sources. So, of course, gravitational waves will be very important to probe all this part of the parameter space, specifically where there are mostly mergers, while X-rays will be very, very important to probe accretion, because usually the clear detection of an X-ray is a smoking gun for the presence of an accreting supermassive black hole or a black hole seed. So, of course, these future missions will be really able to probe all these part of this parameter space and really possibly discriminate between gas accretion and mergers in the growth of black holes. So why is it important? Because we could be able to discriminate between light seeds, so seeds that are formed from POP3 stars, and heavy seeds formed, for example, by a DCBH, so direct collapse black hole. So in these plots, again, there are shown the flux limits for AXIS and other missions. And this plot was calculated assuming light seeds only in the very early universe, while this very similar plot was calculated with heavy seeds only. And as you can see, AXIS should be able to probe this part of this parameter space, so low mass and high redshift. And this part of the parameter space will be fundamental, actually, to discriminate between seeding models, because as you can see, this is the part of the parameter space that mostly changes if we consider light seeds only or heavy seeds only. We're not the only paper that studied how X-ray emissions can really be important to start to discriminate between heavy and light seeds. For example, this is a very nice paper by Ricarte and Natarajan about 4 years ago. And here you see luminosity functions at redshift between 6 and 12. Originally, this plot was made with the Lynx limit only, of course, because it was 4 years ago. I added approximately the limit for AXIS that you can see in this plot with dotted lines in black. And as you can see, between redshift approximately 8 or 9, I would say, and 12, there is a very significant difference between the luminosity functions in the heavy seeds only and in the light seeds only models. So AXIS should really be able to discriminate between seeding models at high redshift, as we were also pointing out. So in our paper, we suggested also an additional way to probe accretion versus mergers across cosmic time, and this employs spins. So if you assume that growth via accretion happens mostly via stable accretion, then you expect that these black holes would spin fastly, like high mass black holes at high redshift, while high mass black holes at low redshift, where most of the mass is happening via mergers, like also in this part of the parameter space, should be spinning at a slower pace. So we actually tested this hypothesis at low redshift, because we do have measurements of spins or supermassive black holes only at redshift certainly lower than 1, or basically lower than 0.1 actually. And you can see as the mass increases, then the median spin parameter that was calculated binning these black holes in mass seems to be decreasing. So as you get more to the merger dominated regime, you see a significant decrease in the spin parameter of the black hole. So of course, this is not a final confirmation, but we would need especially a higher redshift and a larger sample of supermassive black holes with spin measurements to actually test this model. But in general, the takeaway message of this paper was that in the nearby universe, smaller black holes grow via accretion mostly, and larger black holes grow via mergers. Like instead, in the distant, so high redshift universe, the opposite occurs. So wherever you see accretion dominant, that's where axis can really play an important role in discriminating seeding models in the high redshift universe. Now, in the last 4 minutes or so, I will be talking about a much closer volume, so space, basically in our own galaxy, the Milky Way, and what we were trying to do with a very, very talented undergraduate student, Brian C. Paul, and also with Ramesh Narayan at the CFA, we're trying to understand what's the radiation that is emitted by intermediate mass black holes of 10 to the 5 solar masses that could possibly be wandering inside the Milky Way. So we used a standard Bondi accretion model, and these are the main parameters of the model: the density of the interstellar medium, the velocity of the perturbers of the black hole, and the sound speed of the interstellar medium. The mass is fixed at 10 to the 5. And we actually accounted for convection and turbulence with parameters that are derived from simulations. And it turns out that the actual accretion rate onto the intermediate mass black hole is lower than the Bondi accretion rate. So to perform this study, we considered 5 different Milky Way environments: the molecular cloud, cold neutral medium, warm neutral medium, warm ionized medium, hot ionized medium. And each of them have characteristic number density and temperature ranges. And all the results in this paper were weighted via with volume. So meaning that molecular clouds, for example, are very, very rare. They occupy 0.05% of the volume of the Milky Way, while hot ionized medium occupies almost 50% of the Milky Way itself. Before going to the results, I just want to show you the accretion rate distribution that we obtain in this calculation. So basically, we are imagining to throw 1 million intermediate mass black holes of that mass in the Milky Way, and we are calculating for statistical reasons. We are not saying that there are 1 million intermediate mass black holes in the Milky Way. We are calculating what accretion rates in the 5 different environments we obtain. And as you can see, all accretion rates that we obtain are strongly sub-Eddington. This is the Eddington rate, with rates that are maybe 10, 12 times lower than Eddington. So this is an ADAF regime, accretion-dominated accretion flow, advection-dominated accretion flow. And these are examples of some spectral energy distributions with 5 different Eddington ratios. So an Eddington ratio 1 means that the Eddington rate is equal, the accretion rate is equal to the Eddington rate. So they change as you change, of course, the Eddington ratio that you are calculating. And now we are working on better predictions for SEDs and the presence, absence of broad emission lines. So last step before showing you the slide results, I need to define what is observability. So as I said before, we imagine to throw 1 million intermediate mass black hole in the Milky Way. Again, we're not saying that there are 1 million such objects. This is just a statistical analysis. And say that a number of n obs of these black holes were actually observable in a given band, for example, in the X-rays with axis. So the in-band observability is defined as a percentage, of course, n ops over n dot. Now let's go to the results. Finally, these are results only in the X-ray given the audience today, but if you go on archive, there are observability fractions spanning from radio with NGVLA to X-rays, of course, in the whole spectrum. So as you can see, axis should be able to detect about 38% of the fluxes that are generated by this putative population of intermediate mass black holes in the Milky Way. So what you can observe is everything that passes through molecular clouds and cold neutral medium, because they are densest environments and they're also warmer, but you can't observe a hot ionized medium because the fluxes are very, very low. So we also developed some very, very basic selection criteria, especially we calculated the alpha X and also a newly defined alpha SO. So alpha SO is the optical versus sub-millimeter. And as you can see, they of course strongly depend on the Eddington ratio, but these selection criteria could be used to actually pre-select some candidate sources that are interesting, because the same object, of course, will have the same Eddington ratio at a given time. So comparing these flux ratios could be helpful to discriminate between sources. So finally, I just wanted to mention that basically this is for Chandra, but this is true also for any other band that we analyzed. The observability by environment shows that these sources are always observable in molecular clouds. So if an intermediate mass black hole passes through a molecular cloud, say with a typical dimension of 100 parsec and 1 million years of crossing time, they will be observed. And by the fact that we haven't observed them yet, we calculated also an upper limit on the number of such sources wandering in the Milky Way. So to summarize, axis can play a very fundamental role in detecting unobscured and obscure population of heavy black hole seeds, and also in discriminate between light and seeding model. It will be very important as most of the accretion across cosmic time happens above 10 to the 4 solar masses, and this will be visible via axis, and also to detect possible intermediate mass black hole wandering in the Milky Way galaxies or in very nearby galaxies. So thank you very much for your attention, and I'm happy to take questions.
Okay, great. That was a really nice talk, Fabio. So I'll ask one question while people are thinking about what question to ask, and please raise your hand so I can see you in the chat. So, there's been a ton of really, exciting results with JWST on detecting the most distant galaxies. So how important do you think, looking at some of these distant galaxies that JWST finds, as opposed to just doing, a deep or an intermediate survey or whatever, will be in terms of constraining things?
So I think it will be very important once we focus on some candidates. Once we have a clear idea which galaxies are really so far away, it will be very important to look at these galaxies with a deeper view, for example, with axis, to understand what high energy processes are underway in that galaxy, if there is a supermassive black hole or not. And that would be the first detection of a quasar so far away. Because so far they just detected the galaxies, but we need to understand if they are hosting actual supermassive black holes, and axis and similar missions will be really fundamental to study this. So for example, in December, we put out 2 candidate galaxies at Redshift 13. That was before JWST HD1 and HD2. And we just got, with Nico, Adi, Ford, we got Chandra time to observe one of these 2 sources to understand if there is a high energy photon. So I really think that deep observations with axis of these galaxies, once we figure out which ones are actually so far away, will be very important.
Great, and I can see in the chat that Nico is asking sort of about the second part of your talk about the relative velocity distribution between the black hole and ISM.
Yes.
What did you assume?
So the relative velocity distribution is very important, as Nico was pointing out, because you know, the Bondi rate is determined very importantly from the velocity between the perturbers of the intermediate mass black hole and the ISM. So we use the distribution of velocities that was calculated by Weller in 2022. This is another paper that we did with Lars Ehrenquist, and we used the illustrious TNG simulations to study the velocity distribution of intermediate mass black holes proxies with respect to the Milky Way galaxy. So we studied many proxies, so many objects in the intermediate mass black hole mass scale, and we studied the velocity distribution, galactocentric one, with respect to the galaxy and with respect to the interstellar medium, so the gas particles around that. And quite surprisingly, the velocity distribution the velocity distribution with respect to the ISM is lower when compared to the galactocentric velocity distribution. Galactocentric velocities are typically, I think, 100, 200 kilometers per second, while the peak of the velocity distribution with respect to the ISM is about 80 kilometers per second. So that helps also in detecting these sources, because lower velocity means higher accretion rate.
Okay, great. And then Chris, did you have a question?
Yes, very quick question. And firstly, thanks for such a nice talk. And it's really encouraging to see that Axis can say something about the seeding of supermassive black holes. In those calculations, what were you assuming for the bolometric correction from X-ray to sort of the full luminosity, or you know, X-ray to M dot?
Yeah, those are classic bolometric correction that are found in the literature. I don't remember the name of the paper right now, but it was a paper 2018, 2019, and it was named updated bolometric corrections for supermassive black holes. I can send you the paper, actually. Okay, I just don't remember the first author.
Yeah, the two approaches. One would have been to assume some blanket value of 10 or something. But then the concern with that is always, if you go to very, very high, or go to sources that are very close to the Eddington limit, we think that they become relatively X-ray weak. So, but if it sounds like maybe that was already accounted for if you used.
Yes, I think for slightly super Eddington accretion regime, you go lower than 10%. I think the bolometric correction at that point was in the order of 2% or 3%.
Yeah, and that was already folded into those calculations.
Yes. Mm-hmm.
Thank you. Very, very nice.
Okay, great. So let's actually switch right now, but you can post if you have any other